This lecture is on chapter 10, section 2 of our text, and it talks about annuities. So there's some definitions first. So the first definition is, what is an annuity? An annuity is a sequence of equal payments made at regular intervals of time. And there are two types of annuities we'll get to shortly. And the payments that are made are called rents, and we use the variable R to represent rent. So the two types, the first one of annuity is future value of the annuity, and the second one is the present value of the annuity. And I know you can read it, but I'm going to read it for you. The first one, future value annuity, it says the amount in an increasing annuity gets larger with each payment, and the final value is called the future value of the annuity. Okay, so you're trying to figure out basically what that does. You'll see an example here shortly, is when you're putting the rent in, right? It's going to say what's going to happen in the future. What is like the balance, you could say, in the future. The other type of annuity is called the present value of the annuity. The amount in a decreasing annuity gets smaller with each payment, and the amount at the beginning is called the present value of the annuity. What the present value of the annuity does is it gets smaller because the rent that you're pulling out, you put money into an account, and the rent that's happening, the rent is getting paid to maybe you, for instance. Okay, the account's getting smaller and smaller and smaller, all the way till it depletes in the end. The future value is the opposite. It doesn't start with a lot, and you keep putting in, and then you're left with the future value. All right, so let me give you a couple definitions of the two types. So the first one says, parents decide to deposit $100 at the end of each month into a savings account for the college education of their child. After 216 payments, the account will contain $38,735.32. So you think about it, this one is like basically you're putting things into it and you're continuing to build. It's almost like a bank account, right? But it has a special percentage that it's gaining. And you just know that, okay, after this many payments, we'll get this. If based off what you're doing, is it gains this much interest throughout the whole time, and we're going to make a $100 deposit, which we'll call rent, every month at the end of every month. Then after 216 payments, you'll have this $38,000. All right, and if you think about, well, why is 216 payments? 216 payments is 18 years, and the normal student graduates college at 18 years old and goes to college at 18 years old. All right, so this would be someone would start right at the child's birth. Number 2 says, you have just sold your house and deposit your profit of $258,627.80 into an account, so you can withdraw $5,000 at the end of each month for 5 years, at which the time the balance will be $0. All right, so this is now your other one of it being a present value of a decreasing annuity. So the present value is a $258,627.80, but then the rent that's paying, it's paying it to you. You're withdrawing the rent to you is the $5,000. You get that for every month for 5 years. All right, so I'm going to go into a little more detail. So the future value of an increasing annuity of n equal payments, so we could say of, the example was 216 equal payments, is the value of the annuity after the 216th payment. So if you look back at our example, the rent was $100, right? Because you're paying $100 into it every month, and the future value is the $38,735.32. So again, 216 equal payments. It gives you the value of the annuity, which is $38,735.32 after the 216th payment is made. Anywhere in between, this is not the value. Let's clear up the next definition. The present value of a decreasing annuity is the amount of money necessary to finance a sequence of annuity payments. That is, the present value of the annuity is the amount you would need to deposit in order to provide the desired sequence of annuity payments and leave a balance of 0 at the end of the term. So what you're basically doing is you're taking this money, some sum of money, and then you're trying to say, okay, I want to be able to withdraw this for the next 5 years every month. How much would I get here? And then you can figure it that way. So this goes to our second example. Has a rent of $5,000, right? The rent is coming to you now. It's a withdrawal. And the present value is what you start with, the $258,627.80. So how do you find the future value? So suppose an increasing annuity consists of in payments of some kind of money with rent, R dollars each, so the rent. Deposit at the ends of consecutive interest payments into an account with interest compounded at a rate I, which we've already talked about in the previous section, per period. Then the future value, F, of the annuity is given by the formula. Now there's one thing I want to just refresh with you and define I. I is your rate over your N, right? So your N was your number of times it was compounded per year. So if it's annually, it's 1. If it's semi-annually, it's 2. Right? Quarterly is 3. Monthly is 12. Weekly is 52. Daily is 365. Those are the common ones. All right, so our first example. Our first example says calculate the future value. So I know that I'm talking about future value here. Calculate the future value of an increasing annuity of $100 per month for 2 years at 6% interest compounded monthly. Okay, so right away, the $100 per month, that's your rent. So our R is $100. Now in our formula, we needed R, or we can find F, or we have N, and we have I. Well, it asked to calculate the F, so we know we're trying to find F, the future value. We found R, our rent, and now we need to find our I, and then we also need to find our N. Okay, remember, our I is the interest rate, the rate per period. So our I, again, is our rate over our N. So we're going to say 0.06 because it's 6% over, and it's compounded monthly, right? So we go over 12. And this gives us 0.005. So here's the piece that we need right here. And then here's the other piece that we need. And there's one more. And we need to know our N. Okay. And our N is how many times it compounded monthly and then the duration of it. Right? So in this case, it is 2 years monthly. So we have 24. I think I have an error on the last side. I should be an M. I'm sorry. I just realized I said N, not M for I. We're staying consistent with our variables that we've been going with. So now here is our third piece that we have here. So we have R, we have our I, we have our N, and now we can substitute into our formula. So our formula, F equals 1 plus I raised to the power of N minus 1 all over I, and this is all times R. So this equals, now I'm going to substitute in. So 1 plus our I is 0.005. Our N is 24, so to the 24th power, minus 1 all over I, which is 0.005, times our rent, which is 100. So now you're going to plug this into your formula. Sorry, it's already in your formula. You're going to plug this into your calculator. I apologize. And if you're using like a TI-30, all right, I'm going to write it right below it how you should plug this into your calculator. Okay, so you're going to put in, I'll write it in this pinkish color. You're going to have your parenthesis, another parenthesis, okay, and it's going to be 1 plus 0.005 in the parenthesis. That takes care of your first part, and then you're going to put the little caret to raise it to the power of 24. Minus 1. Close the parenthesis, so that takes care of your numerator. You can divide by 0.005. In fact, you can exclude that first 0 just to have it. And then you can put times 100. And then, of course, enter or equals, depending on what calculator you have. And that will give you $2,543.19. Remember, you're always going to round to the nearest penny, which is 2 decimal places. So this is the future value at the end of 2 years at a 6% interest compounded monthly if you put $100 in every month. Okay, so you're making a payment, you're making 24 payments, your rent is $100 you're paying, so what you're really paying is $2,400. And in 2 years, you're gaining $143.19. That would be the difference. All right, now we're going to move to our next problem here. Notice how this one, we needed the future value. This example is a little different. So this says, Ms. Adams would like to buy a $300,000 airplane when she retires in 8 years. How much should she deposit at the end of each half year into an account paying 4% interest, compounded semi-annually, so that she will have enough money to purchase the airplane? So let's go through and find what we have. First, we have F. F is $300,000. So this says she would like to buy a plane for $300,000. She's trying to find out her rent. So the R is what we're trying to find. So in this case, this is what we're trying to find, our future rent. That's what we're trying to find. So we do not know R. Our I is our interest, which is 0.04 over the number of times it's compounded in a year. So it's semi-annually. So that's 2. And they give us 0.02. Next, our N is how many years. So the duration of the year. So it's 8 years exactly. And it gets compounded semi-annually. So we have times 2, which gives us 16. So here is our F is 300,000, our I is 0.02, and our N is 16. Now, when we substitute it into our equation, it says F equals 1 plus R to the n power over I times R. All right, when I plug this into, not plug in my calculator, I'm sorry, when you start substituting in, you're going to get, I'll write it right below it actually. My F is $300,000. It's 1 plus R. Our R was, our small r, our rate was 4%, 0.04. Sorry, I didn't mean to do that. 0.04 times my N, which is 16, all over my I, which is 0.02, times my rate, my rent. I do not know what my rent is. That's what we're trying to find. So what you need to do, we're going to go up here, is it looks like this. I'm going to write this out so maybe I'll explain it too. So you have $300,000 divided by, what you're trying to do is, if you look at this, this is being multiplied. R is being multiplied. So how do you undo multiplication? The inverse operation of multiplication is division. So we're going to divide both sides by all of this. So instead of me making it a fraction over a fraction and making it look really sloppy, I'm just going to say 300,000 divided by, it would be the 1 plus 0.04 to the 16th power all over 0.02. And you put that in the calculator just like that. And what you get for R is, your actual calculator gives you this, 16095.03776. For those of you that are trying this is what your calculator does give you. But remember, we're talking about money, it's rent, so we need to actually round to the nearest penny. So in this case, it's about $16,000 $95.04. So every half year, that's what Miss Adams needs to deposit every half year in order to own a plane when she retires in 8 years. All right, so we have present value and rent. So the present value P and the rent R of a decreasing annuity of N payments, so how many payments you have with interest compounded at a rate I interest per period are related by the formula. So here's now a new formula. So let's go through and try to figure out the difference between these problems. How much money must you deposit now at 6% interest compounded quarterly in order to be able to withdraw $3,000 at the end of each quarter year for 2 years? So this is more like our second type of problem. We're going to have a lump sum in an account, and we're just going to withdraw it. So we're going to let it sit, gain some interest, and we're just going to make sure we can withdraw it, right? So first off, let's identify what we have. We have our rent, which is $3,000. Our I is our interest rate, which is 0.06 divided by our N, which is 4 because it says quarterly. And that is 0.015. And our N is quarterly times the number of years, which is 8. So again, here's our 3 pieces. And we're using our new formula now. Our new formula says P equals 1 minus 1 plus I to the negative N power all over I times R. So now we substitute values in. I'm just going to keep going equals because we're going to find what the present value is. So I have 1 minus 1 plus I, which is 0.015 to the negative N, so it's the negative 8 power, all over I, which is 0.015, times our R, which is 3,000. And again, you're going to substitute that into the calculator just like that, and that gives you 22,457.77524. And then when we round it, because we round to the nearest penny, which is right here, $22,457.78. That is what you need to deposit if you want to withdraw $3,000 at the end of every quarter year. So every 3 times a year, you're going to withdraw $3,000 for 2 years. I'm going to have to apologize. I just had a massive little lapse while I was doing this. I realized that on this problem, I did this incorrectly, so hopefully this doesn't mess you up too bad. This value right here should not be 0.04. This value needs to be this 0.02 because that's supposed to be I. Because I wrote this wrong. This should be I, not R. So I'm going to fix this, and I sincerely apologize. This should be I. So when I substitute it in, then this changes to 2. And then this changes over here to 2 as well. And then you actually get that answer now. So if you're trying to do the calculator, I have it down right. Yep. I sincerely apologize. All right, so now we're going to move on, and we're going to have no more errors. All right, in fact, this is our last example here. So this one now says, if you deposit $10,000 into a fund paying 6% interest compounded monthly, how much can you withdraw at the end of each month for 1 year? So again, it's still our second type of annuity. We're still withdrawing, but now we're trying to find our rent. We do not know our rent. How much can we withdraw? So say I have this amount, and there is this fund that pays 6% every month, and I want to draw money out each month. How much can I actually get out of this? All right, this is what people will do if they're on, say, a budget or they inherit some money and they're going to live off this. Some people want to retire early. They say, you know what? I don't have much, going, and I feel like if I had this much money, I mean, hopefully you have more than $10,000 to live on when you get to that stage of life. But hopefully you can look at this and say, well, this is how much I want to be able to gain out, and this is how much I think I'll be able to, my longevity of my life, and this is the kind of problem you would look at. So first off, we look and we say, what is the present value? So our P, our present value, is 10,000. Our I, we're going to say our interest, which is 0.06, over our N, which is 12. I said N again, I meant M, 0.005. And then our N is how many times is it compounded per year? It's 12. And we're only looking for one year. Right, so that's just 12. So now we substitute our formula. And when we're trying to find the rent, it does make it look more complicated because there is more work to do in the calculator part of it. But if you get comfortable with the calculator, then it's not as bad. So I'm going to rewrite my whole equation, the general form. P equals 1 minus 1 plus R to the negative N all over R times. I did it again. I am messing up big time. I'm trying to remember. I thought I remembered it, and I don't. And I look it back in my notes. I keep writing R instead of I. I apologize. So now you're going to substitute all your values. I'm going to substitute right below it. So my P is 10,000 is 1 minus 1 plus your I is 0.005. N is 12. Don't forget there's a negative there. And then your I is 0.005 times R. Again, we want to isolate R. And so since it's being multiplied to R, we want to do opposite, which is divide. So we're going to divide all of this by both sides. And it's going to eliminate this one, but then we're going to basically move this underneath here. But instead of writing a fraction divided by another large fraction, we write this. R equals 10,000 divided by 1 minus 1 plus 0.005 raised to the negative 12th power all over 0.005. And when you plug that into the calculator, you get a longer number, of course, than we need, but I'm going to write it out. Or we need dollars here. So we're going to say $860.66. That's how much, if you deposited $10,000, you can pull $860.66 out every month for a year. All right. Now, summary. Our summaries here. We talked about increasing and decreasing annuity is a sequence of equal deposits or withdrawals made at the ends of regular time intervals. The reason why I put it in parentheses is decreasing goes with withdrawals, right? And then increasing goes with deposits. F is your future value or balance at some time. R is your rent. And then here's your formula for the future value. Then you have your present value of a decreasing annuity is calculated with, here's the formula. And then what I added is in this section, it goes over it, but I feel like you can just see this. It says successive balances of an increasing annuity can be calculated with this. So if I do 1 plus my interest times my previous balance, right? Then I add my rent to it, then I get my balance of my new. That's if I'm increasing. Now, if I'm decreasing, then I'm subtracting the rent. And that's what you do in the background the whole time. Right? That's really what you're doing, but you're just calculating it for so many years really fast.